Hello and welcome back to the lab. To everyone who is subscribed, thank you for being here with us in the lab. I was not sure what to expect when I posted the first video about repairing a joystick, but here we are. I'm glad that this community is finding these videos helpful and informative. This community is why I will continue to make videos, so thank you again for being here. If there are any pieces of equipment that you'd like to see restored, let me know and I will see what I can do. Also, if there are any topics you would like to cover, I'll see what I can make happen as well. As of now, there's a lot of Tektronix restorations that I have completed. I'm planning on branching out into other vendors of test and measurement equipment. One of my goals is to blend the old and the new to get the best of both worlds. This includes digital and analog. There are some things that the digital domain is better at than the analog domain, but also the reverse is true. But definitely let me know what you would like to see, because this community is nothing without you all, so once again, thank you for being here. Today on the bench, we have another piece of Tektronix oddware. I'm actually going to be doing the restoration on an AM502, but I figured I'd get a 7A22 out as well. The front panels look a little different, but essentially they're the same thing. So the AM502 is a TM500 plug-in. So it'll go in a 500 or 5000 power frame. The inputs are over here, and the output will go out to a scope so you can watch. The 7A22 is actually a 7000 series plug-in to go directly into a scope. So this is in the queue to restore at some point in time, but today we're going to work on the AM502. They are both differential amplifiers. So I will get everything set up, get everything warming up, and then we'll get our calibration document, and we'll see if we can't get this thing started. While I wait for some of the gear to warm up, I'm just going to do a quick visual inspection of this, just see if I can't figure out anything that's going on with it. We do have a cal sticker from Tektronix themselves, which is back in, my due date is 99, so this was done in 98. So kind of an old unit. This one was also property of the Navy, and it looks like also the University of New Orleans. So it's had a decent trip to wind up here. Pop the covers off. Not much on the back side. A couple caps and some switches. Things like that. I'll be sure to grease some of these shafts, make sure they're got some oil on them, and that's an interesting arrangement. The pot into the coarse and fine. So the coarse pot is back here, which is a wire wound, I can tell by the feel. And then the shaft actually goes through the other pot, so mechanically that's an interesting design. What do we got on the other side? Well, there's all the magic on the other side. There's our big input caps. These are the protection fuses for the inputs. There's lots of adjustable capacitors up there to get this thing into spec. Still a lot of discrete components, individual transistors. There's 2 ICs here, but a lot of discrete stuff still in one of these. So I did get some questions about this brick that was on the back of the AA501 while I was repairing it. This is actually a disassembled TM502A. I've taken it out of the case. Here's the chassis for it. So the front comes off, the power supply just slides out the front this way, but it all slides out as one piece. But it really gives you good access. Might not be able to handle a 3-bay plug-in, because if you need 3 power connectors, it's too short. But anything 2 or less, really convenient if you're going to do a lot of 500 work, to see if you can find one of these. This one has the newer style the newer style powerlytic capacitors. So I haven't changed those yet. Everything's still good with this. So we are good to go there. I also got a question on the power supply for a TM500 module. The main bulk power filtering and ripple and the main DC supplies for these TM500 plugins are in the power frame. So the bulk filter caps and everything, they're in this module, not this module. That's why I don't change a lot of caps in these, is because they have a little bit of regulation in them. Some of the modules have their own regulators, like all the meters have their own regulators and things in them. But the bulk of the rectifiers, the bulk filters and everything are actually in the power frame themselves. So that's why I don't change out as many electrolytics in these as I normally do. I'll be checking this one for electrolytics because there does seem to be a lot of them, so I'll at least be giving them a visual inspection to make sure nothing's gotten too warm, overheated, been dumb, and make sure none of them are leaking because I want to get it repaired for the long haul. Of course, I say that, and in doing a visual inspection on this, I do think I'm going to change out these electrolytics, this one, this one, this one, this one, this one, and this one, because they are looking a little rough. They've got some corrosion on them. Some of them are starting to dome up, things like that. So they've got some time on them. So I'll fire up the desoldering irons, and then I'll get all those replaced, and then we'll see about doing a calibration. Okay, as with all calibrations, we start with the power rails. So I have the 7510 hooked up to the 15 volt test point, and we're doing positive 15 volts first. The adjustment is R916. No, I'm sorry. The test point is R916. The adjustment is no adjusting, just regulating. So I need a voltage reading between 14.25 and 15.75. I have 14.48, so power rails in spec. We'll check the ripple on it. My ripple's running about 0.1 millivolts, so we're perfect there. We'll check the negative rail now, which is this resistor right here. It's that test point right there to chassis ground. Let me get a non-conductive pointer. The plus 15 volt test point is right here down at the bottom, so it's the exact same resistor, just down 2. So that's 15, not the green one, but the one below it. That's plus. We're on minus. Ripple's 0.16. Flip this back to DC. And we are at 14.51 negative, so we are in spec there. Need to check the 5 volt test point now. The 5 volt test point is this resistor right here in the middle of these other two. It's kind of hard to get onto that one, so I shut it down. I'm letting it warm up now while it takes a reading. And my spec is 4.5 to 5.5. We're at 478, it looks like. Yeah, 478, so we're good. I'll shorten up these times in editing, but I'm waiting on the meter to update and things like that. So, but these videos tend to be kind of long. A time will have elapsed to allow the meter to stabilize, the unit to stabilize, but through the magic of the camera and editing, it'll just progress quickly for you guys. Okay, so I'm going to zoom in on the scope. It's just a 50 ohm cable into the input of the scope. I have the scope set to ground over here. I'm going to rotate the gain knob, and I'm looking for less than 3 divisions of movement from center between the top end and bottom. We're working on the step gain AC balance. So I'm going to zoom in on the scope, and we'll see what happens. All right, so that's good. little bit of movement. It's not moving. Okay, I'm going to check the step gain AC balance. I have the AM502 is set up in the preliminary instructions of the calibration procedure. 1 volt, 500 microseconds. I'm going to rotate the gain knob, and I need a trace shift of not more than 3 divisions. It's moving. Yeah, that worked. Wow, that's touchy. That's too touchy. Okay, that switch needs some cleaning. So let me clean that and I'll bring you guys back. And there they are in all the glory. One of the most pain in the butt parts about restoring Tektronix gear, these micro switches. They work really, really well. They get a little bit of dirt on them and they go out to lunch. I had to take the cam out. This rides inside that shaft. I'll oil this while it's out. That way I can get the through shaft is for the variable, which is here. So the through shaft connects here. Cam switch is here, and then the shaft goes to the front of the unit. On the front of the unit, you don't have to take it out, but you have to loosen this nut to get it to tilt up so you can clear the switches so you don't bend the switches when you pull the cam out. But that's how you get that apart. I'm going to clean these, and when I'm done with that, I'll get everything put back together, and we'll see if it made a difference. Okay, and we're back. Get some readout, show trace. I'll rotate the knob. Nothing. We are within 3. We're good. And just to show that the switch cleaning worked, wiggle, 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 wiggle. Nothing. Rock solid. So, perfect. That is working. So, now we need to check the variable gain DC balance. So we move this to 0.1. Center this. Right there. Actually, let me get right on it so I don't have a parallax error. There we go. Now I need to rotate the variable gain. That's about 0.1 division, but I can probably do that a little bit better. Let me work on that. I gotta move the camera out of the way for that one. The adjustment is R269, so it's actually right here on the board. That's the one I need to adjust. So let me get that adjusted, and I'll be right back. Okay, the adjustment pot is right here. So this is what we were adjusting, and I'll show you the result. That is stop to stop. Fully counterclockwise, fully clockwise. So we got it even better. So, very good. Okay, so I moved the low frequency down to DC, and I'm adjusting the DC gain, the step gain DC balance to the same position as it was at the end of step 5. Sorry, I need to redo that. I got a step ahead of myself. So let me set that back up. I got to go back to step 5, set that back up, and then I'll be back. Okay, I'm set back up. So here we can see this is moving. That's good. Now we're locked in. So we note the position of the trace. I'm going to zoom in. Actually, no, I'm not, because it's going to freak out, but it's dead on graticule center. Going to set the scope to 10. Now, instead of doing the step gain, I have to adjust R191 to bring the trace back. Oh, that's a noisy pot. Just bringing it down very slowly. Let me move that a little bit to clean it up. I'll be right back. Okay, and there's our end result. It's about as good as I could ask for. All right, so 2 volts per division. Set this over to DC. Gain switch to 10K. Okay, I need to adjust 461 to bring it back down to center. There we go. And so you guys can see as well. At least on my unit, this is R461, so this is what I adjusted to bring it back down into center. Okay, the next thing I got to do is I got to connect a 50 ohm terminator to the positive input. A 50 ohm terminator, not a through terminator, so just a 50 ohm resistor to ground. This is a cheap one. That'll probably be the next thing that I add to the lab is some good 50 ohm terminators. I have good 50 ohm pass-throughs, just got to get some good 50 ohm terminators, but we'll go with it because it's what we got. And we're back to 0.1. Release the ground from the plus side. Now we need to adjust the plus input gate leakage current compensator, R105. R105 is right here, and it's going to be a play with it because you adjust it while pressing in and releasing the AC plus push button for minimum trace shift. Okay, where's my trace? There's my trace. Turn that down a little bit so we don't burn the tube. Alright, where's my resistor? Resistor is here. I don't have a lot of trace shift, so that's good. This should not be a crazy adjustment. Ooh, way too much. Nothing. So my reference is about, I'm putting the trace right at about 0.2 divisions. If I actually trigger this on line, it should stabilize. Look at that. We're looking at line noise. So since we're seeing a little bit of line noise, we can, since the trace is now stable. All right, there's in. That's about as stable as I'm going to get it. So I'm going to call that good right there for that adjustment, because there's now very little movement. Yeah. All right, cool. Okay. Back to internal. Ground back out the plus, move the terminator over to the minus. And we do the same thing. Our other adjustment is right here. The negative input gate leakage current compensation. Try saying that 3 times fast. So, alright, we'll position this back to middle. We will line trigger. And because we're on the negative side, our trace is going the opposite direction, which is fine. Target that right in the middle. Take off the ground. Move it back to center. Yes. And then AC. Ooh, that needs some adjustment. Okay, that's the minimum I can get. Okay, so vertical amplifier gain to 0.2, gain to 100, high frequency negative 3 dB to 1 megahertz. Okay. Connect the calibration generator to the AM502. All right, 5 divisions of display. Spot on. Okay. So now I need a 50 ohm terminator and a 10x attenuator, because this will knock the signal down by 50%. Going into plus. So we've got the PG506 coming down, feeding the AM502 through a 10x and 50 ohm attenuator out of the 502 into the scope. Okay, so DC gain. Gain is R159, which is right here. And we are running a little hot on the gain. Wow, that is really touchy. That control needs to loosen up a little bit. There we go. Gotta clean that pot. It's a little dirty. And after cleaning the pot, there we go. Picking up some noise in it, but after cleaning the potentiometer, it hit exactly where we needed. Perfect. Okay, if I rotate the calibration control fully counterclockwise, it should go less than 2 divisions. It does. All right, so let's go to 0.5 and turn up the gain. That looks good. 0.2. Turn up the gain. That looks good. 0.1. Gain's now at 1K. That looks good. 50 millivolts. 2K gain. Yep, still looks good. $20 millivolts. Starting to pick up a lot of noise. Again, this is that chirp that keeps happening in the lab. This is, I gotta find that. This thing's nuts. I don't know where that's at. 10 millivolts. Yep, looks good. 5. Yeah, looks good. 2. Looks good. This is also super noisy because it's all open to the noise. 1 millivolt, and we're at a gain of 100,000. There goes the chirp. When I had it, it looked good. Okay, this is just checking the divide by 100. Gains at 10K, divide by 100's in, and we're 1 volt going into the calibrator. It wants me to check the negative, so this should flip the polarity. So we will unground that. We will ground the plus, put it into the minus. And that checks our gain at the minus, so we are good there. Okay, setting up the AM503 for the next step. Divide by 1,000's out. All the input ground buttons are off. And AC is in. Low frequency negative 3 dB is DC, which it is. And the gain is to 100. Okay, we have fast rise from the calibration generator coming in. 1 kilohertz periods. I'll show you guys the setup of the scope here in a second. Here's how the scope's set up. 2 microseconds per division, 1 millivolt per division. This is the display we get. We're looking at this front corner, and we want to adjust C222 for best square corner. C222 is right here, so I'll be adjusting that. This is the smaller of the 2 capacitors. Okay, so if I back it up, we have some this is what I'm adjusting. So optimum square corner is what I'm looking for. Just like that. So that looks great. All right, we have to do the exact same thing. Just need to move this to the negative port because we need to adjust C122. C122 is right here. So I'll be adjusting that right now. Same thing. Nice square wave. Exactly the same way we adjust a scope probe. Just like that. And that is the cross neutralization. Next is the input capacitance. I will need to get a normalizer. This is kind of a rare one. I don't use this one much, but I need the 47 picofarad 1 megohm RC normalizer. So the number on this one is the 67, which means it's a calibration fixture, but then it's the 0541. But yeah, all it is a resistor and a capacitor in there. Okay, we're doing the exact same thing, except we're updating C50. Exact same thing, tuning the best square corner. It's a little light. It's overcompensated. So, we need to speed this up a bit. Try to get a good angle and a good connection to this. Overcompensated because I am not using a plastic tool. Which is terrible. Let me get something plastic. The screwdriver is too inductive. Alright, so we still have some high frequency compensation, but the low frequency stuff is okay. So that's kind of what I'm looking for right now. Everything is nice and flat. Yes, everything's nice and flat. This will probably get adjusted here in a little bit. Got to do the same thing on the plus side, but then I need to adjust C50. No, I'm sorry, C30. So there's C50. That's what we just adjusted for the negative. We need to adjust the positive, so we need to adjust C30, which is this one right here. I got to break it loose with the metal screwdriver first. There it goes. Now it's moving. Now we tune it with the non-inductive one. Looks good, nice and flat. We still have this overshoot here, but I think that's going to tune out later, so we're good, nice and flat. There's what the scope's set to, but that looks good. Okay, so I needed to add the divide by 100, bring this down to 0.1. We're now at 100 millivolts, but I need to pull out the 10x attenuator. 5 divisions of display. And we are way overcompensated, so we need to adjust C32 and 35. So these two right here at the top, those are what we need to adjust. Let's see what does what. This is, first one's going to be C32. Oh, ooh, okay, so that's low. C35 is right next to it. And it says for best response, so that probably means it's not going to be perfect. But it wants best flat top. That's about as good as I'm going to get it. Now we have to do the same for the negative. Yep, got to move the RC normalizer to the negative terminal. These terminals are nice and tight, and that one is pretty out there as well. And I need to adjust 52 and 55. So 52 and 55, these two. $55 is the low frequency. 52 is probably going to be the corner. Yep, look at that. There we go. And it wants it within 0.2 divisions, which we are. So now what we need to do is pop the normalizer off and get into the high frequency common mode rejection. Okay, this is a piece of tech oddware that I had to get for doing the calibrations. This is a dual input cable. It has one B and C on the front, and these are length matched cables to 0.1 millimeters. So very, very tight tolerances. I have done calibrations in the past just to get the stuff up and off the ground and kind of bootstrap its way up using a dual B and C cable. It works. It's not the best, but it does work in a pinch. There's some stuff, so for the AM502, given that it's 1 megahertz, not a huge deal. For the differential comparator, because it's 100 megahertz common mode rejection, you start getting into delay line, it is a big deal. But this particular cable, I had to look for this one for a while, so just be patient. They do come up, and when you see them, jump on them, because these are definitely interesting to try to find. All right, that's on there. Divide by 100 is out. AC and ground push buttons are out. So we're AC coupling this. No, we're DC coupling this. Gain switch is at 100. High frequency negative 3 dB to 0.3. So down 1. And the low frequency dB switch, or negative 3 dB switches to DC, which it is. Vertical deflection goes to 10 millivolts per division. Now I got to set up the function generator for 50 kilohertz sine wave output. All right, I'm going to use my Rigel to set up the function gen. I need 50 kilohertz sine wave at 10 volts peak to peak. Okay, 50 kilohertz at 10 volts. That doesn't look too bad. That is very quiet. So, what do we want to adjust? Okay, so we need a minimum of 1 division or less. Actually, I'm going to detrigger this. That'll probably be easier. So with it detriggered, I'm just getting a ghosting. I want this to be as narrow. The jumping around doesn't bother me. I want it to be as narrow as I can make it to get this into calibration. And I need to adjust C150. C150 is right here. So I want to adjust C150 for the narrowest that I can. Oh yeah. That's going to be it right about there. All right. Well, I'm at 0.5, so I'm 2 divisions now as opposed to 1 at 0.10, but that gives the time base a little bit something bigger to grab, which is why I did that. So anything inside, so right there, see the waveform kind of changes, and then it kind of reverses and goes back. So right there is going to be about my lowest point. So that's the adjustment. Okay, so divide by 100 in, 100 millivolts per division. Come off the function generator, go over to the calibrator, and it wants me to put in 100 volts. Okay, there we go. Okay, a little bit of confusion on step 15. No, sorry, 16. To get the amplitude right, I had to AC couple the signal. Yeah, I checked the DC offset through its entire range, and I get the right, because it tells me to disregard the spikes on the square wave signal when it's AC coupled, so I am going to go with that at the moment. 100 volt square wave. It says don't worry about these. But I am supposed to adjust C52 and R40 for the best display. So C52 and R40. For minimum CRT display amplitude within 1 division or less, best looking display. I think that's what it's looking for. And now that I have RNC set correctly, I can actually finish this adjustment on DC. But I did have to start it on AC. That was a very scratchy pot. But there we go. So that's with the AC buttons out. So that is the way it's supposed to look. Okay, so we're checking the high frequency attenuator. I need... It's a little over. Let me reset this up again. I bumped the adjustment for the function generator, so I think that's the problem. Yeah, I did have it about 10 millivolts high, so that was the problem. So we're going to check the high frequency attenuator. I'm all the way up on 1 megahertz. Yes, so no limit, 1 megahertz to DC. Crank this up to 1 megahertz, that's 10K, 100K, 1 meg. Perfect. That is what we should see. So let's set it to 300 kilohertz. Not adjusting the amplitude, just the frequency. This is actually really going to be annoying. The function generator is okay, but this is not the best function generator in the world. I would much prefer to fine-tune knob. Kick this back. That looks good. Next frequency is 100 kilohertz. I'm using the frequency counter in the Rigol to set the frequency because being that this is only 50 millivolts, my Agilent is kind of deaf. And that looks good, right at 3.4, which is what we're allowed. Actually, it's 3.15 to 3.85 is what we're allowed, so that's right where we should be. Cool. Next frequency, 30 hertz. No, 30 kilohertz. Kick this back by 1, crank this up a bit more. There's 30 kilohertz. Back to the differential amplifier, kick it back. That is, again, perfect. They're running on the low side, but they are within spec. 10 kilohertz. Yep, we're good there. Actually, these attenuators are running exactly, or these filters are running exactly almost the same. 3 kilohertz. Yep. They're running right about 3.2. Perfect. I love it when stuff lines up the way it's supposed to. 1 kilohertz is next. Yep, we're good there. The noise that you're seeing, actually the camera's not picking it up. To my eye, there's a little bit of noise in the trace. The blank spots are actually when it's jumping up to run the readout. If I turn the readout off, the trace goes exactly as you'd expect. Okay, what's next? Are we at 1K? Yeah, we're at 1K, so 300 hertz. Yep, we're still good there. Awesome. Now for the slow one, 100 hertz. Yep, we're good. So the high frequency bandwidth is correct. I need to set the high frequency switch to 1 megahertz now. There we go. And we need to check the low frequency. So 10 kilohertz. Function generator to 10 kilohertz. Still not changing the amplitude, just the frequency. Okay, 10 kilohertz. We should have right about 3.8. And we do. So that's good. 1 kilohertz. Or, I'm sorry, yeah, 3.8, under 3.85 and over 3.15. Yep, we're good. 100 hertz. 0.1 kilohertz, 100 hertz. Yep, we're good there. Next frequency, 10 hertz. Gonna have to do this. I don't have anything that counts that low. I'm actually going to have to do this one with the Rigel. I can't see it. It's too slow. Yes, that is actually working. Let me move you guys up to the Rigel real quick. Here's the Rigel. You will have to take my word for it. I have the time base on 100 milliseconds per division. This is slow. We are at 3.5 exactly, so that's good there. The next one is 1 hertz. So we'll actually just kick this down to 1. And I will kick this up to 1. I'll single shot that actually, because that'll go slower. This is how slow this is. So it's slow. Just shy of 3.6. So we're actually good there. 0.1 hertz positions are tested when you do the other switch positions. So that actually concludes the attenuator test, which is good because it's slow. But now I need to check AC. So we will punch the AC button, single shot that one more time. Hang on a second. Okay, I think something's going on because the signal is so slow that I can't even measure its frequency. It's given my Rigol scope a headache because it's just so slow. However, the measurements are exactly the same for the positive and negative channels. So I think the unit's okay because I'm getting exactly the same measurements out of both channels. But with my current setup, with this gear here, I need something a little slower to just check the AC. DC's working just fine. It's just when I hit the AC, it's just a touch light. It's right at 3. It should be at 3.15. It's very strange. So I'll keep playing with it here, see if I can't get it, and I'll let you know. Okay, found the missing piece of data that I needed. I looked up to see what the specifications were, and I ran across this in the performance check. When you're checking the AC coupling of an AM503, you do it at 2 Hertz. So 5 divisions of display at DC, hit AC, you should get 3.8, 3.85. I'm getting 3.84. Perfect. Let me check the positive side of things. Single shot this. Boom, 3.8. It is perfectly in spec. In the adjustment procedure, they don't actually tell you to use a frequency of 2 Hertz. They do in the performance check. Okay, step 7, the overall noise was kind of confusing. So what you do is you stack 4 attenuators in a DC terminator to the front of the unit, turn the gain all the way up. Then you have to play with it until you get 2 noise bands on the scope. And when you see those 2 noise bands, you then back the amplitude of the fast rise pulse down until the noise bands merge. I had some fun because it was superimposed on a 60 Hertz sine wave for the line frequency, so that was fun. And then you measure the amplitude of the sine wave, square wave fast rise to get the amplitude with 1 attenuator. So there was 4, now there's just 1 in a 50 ohm terminator. So I get 11.8 millivolts with undershoot. And then we need to do noise is gonna be, well, it's actually gonna be pretty easy. It's gonna be 11.8 millivolts over 10 to the plus 3. And I'm going to be at 11.8 microvolts of noise. So that checks out and also jives with what they said typical numbers would be, because the service manual says typical numbers are 12 millivolts, which is 12 microvolts of noise. So we're running a little bit under that, 11.6. 11.6, 11.8, 11.8. So right on par with where we should be. So this unit was out of adjustment, but it is no longer. The caps we replaced and all the adjustments that were made. This unit's nice and in spec. Looking forward to using this for some low-level measurements. The dish of shame. Just some old electrolytic capacitors that looked in not so nice shape. Size-wise, I was actually able to fit in 220 microfarad caps in here, so because these electrolytics were just power supply and rail stiffening decoupling capacitors, I was able to get away with greatly increasing the capacitance available to the regulators and the individual chips. So that won't do anything except quiet down the unit and make it better in the long run, because modern technology, this is a 22 microfarad 25 volt cap, This is a 220 microfarad 25 volt cap. They are just about the same size. So I replaced everything with 220s, and as we saw in the calibration, worked just fine. Everything was serviced in here, switches were cleaned and lubricated, and everything's good to go for the long haul. So I'm going to get the side panel put back on. We'll put a cal sticker on it, and it will find a home in one of my TM power frames. Thanks for stopping by the lab and taking a look at this AM502. If you guys have any comments, please feel free to leave them in the description down below. I do read all the comments. If you guys have any suggestions or anything you want to see, definitely let me know, and we'll see what we can make happen. And I will see you guys in the next video.